Okay. This should be... It should be live now. Apparently there are 2 people watching, according to the Twitch counter thingy. No one in chat though. Not quite sure how that works. Right. And no one in the IRC room either. Not sure if anyone is here at the moment. Let's just spam the link a bit. Someone pinged me on IRC. I have no idea what he wants. Still says I'm streaming Noita or Noita or however you pronounce that, which I'm obviously not. Get this mech out of the way. Yeah, so if there's someone else here, welcome. This is gonna be, so the idea here, I have for a long time wanted to make my own keyboard, like mechanical keyboard. While I was a student, that was too expensive. Now I have, and another thing is that I really like thinner keyboards. So for example, this keyboard that I'm using right now, as you can see, it's pretty, hopefully that aligns well. It's a pretty slim keyboard. So the typical like mechanical keyboards for me tend to be a bit tall. So I guess that's not pronate, that's pronate. Whatever this is called. Which I don't like. My hand hurts when I type on tall keyboards. But Kyle, the company, not a dude called Kyle. Let me switch over here to this cam. So yeah, Kyle, the Switch company came out with these switches, which are low profile switches, and they look a little bit something like this. See, switch back again. They look like this. Pretty tiny little switch. Feels similar to an MX Brown. I have an MX Brown as part of like a switch testing kit. And I sort of tested them against each other, and they are pretty much the same actuation point. Or actuation force, rather. So I took these. Well, I ordered them actually before they became available to the general public. So I contacted Kyle and said, "Hi, so technically I have my own company, which is from when I was studying and doing doing like freelance work. I had my own company for doing that. I contacted them like via my company and said, "Hi, I'm a company in Norway. We would like to see if we can design a keyboard with your new small, like low profile switches." And they sold me. I didn't get them. They sold me a couple, like 100 or so switches with keycaps. And I've made this. It's a split board. So it's two halves. They're all hand soldered, which is a massive pain in the ass. Hand soldered with enameled wire and diodes and stuff. And this, it's slightly taller than my old keyboard, but it feels really great. But the dangly part up here is sort of the focus of this video and probably video series. So what we're going to be doing, we're going to be programming these microcontrollers. We're going to be programming these microcontrollers. This is the Teensy 2.0, which is it's an Atmel. It's basically the same as some of the Arduino chips, but it has more outputs. I don't really need the outputs. They are recommended for doing keyboards with. I bought two of them, one for each half. One is soldered in there, one I have here. I also bought two I/O extenders, which is what is soldered to this one. So as you can see, one has the teensy, the tiny. Let's do this. One has the teensy, this one with a tiny microcontroller. This one has the I/O expander on top. So an I/O expander is basically I2C or some kind of communication protocol that can talk to a microcontroller, and the microcontroller can control the pins through the I/O extender. So that's one way of sort of getting more pins. In this case, I'm using it to move the pins away from, or to be able to separate them via only like the I2C bus, which is just 4 wires. So you could get some nice like interconnect cables and stuff. But that is getting ahead of ourselves here. So let's look at this Teensy. It's AVR, USB based microcontroller, pretty similar to the Arduino. So it's an Atmega 32U4, which I believe is the same as the Arduino Leonardo, if I'm not mistaken. Same as is in the Arduboy, which I've programmed in NIM before, and which I've some of my presentations I've mentioned that and shown some code for doing that. And as we can see here, we can program it with C language, and we can program it with Arduino software. So I've been doing mostly this with the Arduboy that has the Arduboy library. I sort of just wrapped that, and it uses Arduino. It works. It's fine. But then you are sort of doing just a light wrapper on top of Arduino. NIM already compiles to C, and if we write our own stuff in NIM that sort of compiles to optimized C, I think we can even get sort of an edge over Arduino software. We probably don't need it in this case, but it's going to be a fun sort of challenge. The only thing is that this one comes with a lot of, or Arduino comes with a lot of stuff that's ready for us to use, such as an I2C implementation, and some other stuff. C for AVR does not. There is a library for I2C. When we come to that point, I'll see if we decide to go for re-implementing I2C in NIM, which might be fun, or if we just use a library, or if we start using a library and then transmission, if we go over to using something else afterwards. So how are we going to program this chip? So first off, I've made some changes to my camera setup here. So you have me up in the corner, you have the code and everything, but I also have my old webcam set up to point to a tiny portion of my desk over on the left hand side here, where we can see the microcontroller close up. It's nice and sort of focused on that, so we can see the microcontroller. I can also move it sort of further up because now like I can't fit the keyboard in here, so we can move it back later, but for now I'm gonna keep it nice and close so you can really have a look at the chip as we program it. So yeah. So first things first, how do we program these chips? What you're looking at? We're doing keyboard firmware. That's going to be running on the TNC 2.0, which is the chip I've got here, at least for now. And it's going to be powering my custom matrix keyboard. What is looking at the chip? Well, you'll see in a second, but it does. There is a purpose for this. It's basically so you can see sort of just me sitting here talking, showing you the code and saying, yes, it works. Wouldn't be very fulfilling. So the idea with that camera is that I can show the LED on the chip blinking. I can show when I'm connecting wires to it. And later when we get to the keyboard, I can move it sort of further up and you can see the keyboard. You can see me hitting the key and see the output on the screen. So yeah, that's the idea of that. I just have an empty folder here. So there is some setup to this. In order to get NIM to so NIM compiles to C, and then it invokes a C compiler, and that compiles to the TNC. If you follow this, which is like this, super annoyingly is a PDF. It's not a link. So we have to go digging for the actual guide here. I mean, I have this all. Oops, not that one. This is just an extended version. Yes, we are in the store. We don't want to be in the store. Oh, this site is so horribly set up. It's really annoying. Yeah, so this goes through how to set up and work with the TNC, making the LED blink. So it has a bootloader that is enabled by hitting this tiny button. So when you hit that tiny button, the TNC restarts or reboots, and it boots into the bootloader mode. When it boots into the bootloader mode, it basically, I think it's like sends a signal over USB, see if it gets a reply or if it's just waiting for a reply, something like that. And if it's then detected by the computer, it will run the code on the microcontroller, or it will upload the code to the microcontroller, and that will work. So yeah, user program runs when power supply, reboot button clicked in the TNC loader, and in auto mode immediately after download. So download is downloading a program. Half K runs when push button is pressed and released. So if it's powered, we hit the button, it goes into bootloader mode. Or of course, if we jump to it, yeah, and then nothing runs if you hold the button down. Yeah, so we have the TNC loader, which is a stupid GUI program, but we also have a nice command line version, which is what we're gonna be, what we are gonna be using. So it just has a TNC loader CLI, specify the chip, and here is the list of chips. We're using this one, so we're using the Atmega 32U4, and then we pass it a .hex file. So how do we get a .hex file? For that, we need the C compiler. Many of you probably already use GCC for NIM. This is the AVR GCC version, and like utilities and C, like libc, stuff like that. Yeah, and here is a nice like Blinky example. Explains a bit how all of this works. They also have a massive long makefile that we're not going to get into. This we're going to be looking at in a second, and then it just blinks some stuff. And of course the makefile that they provide you will do all of the sort of compile stuff for you. However, we're not gonna be using that. We're gonna be using NIM. So for this, we need two things. We need the nim.cfg file, which tells the nim compiler sort of which compiler to use, what flags to pass, all of that stuff that makes the TNC stuff work. I have looked at the makefile already. I have extracted all of that, and I have already gotten all the flags that we need and checked that everything works, so you don't have to watch me do that on camera. We also need, or I like to use a makefile. So for those of you who don't know makefiles, they are a simple sort of rule recipe kind of format. So it's a rule recipe format, and it checks if the file of the rule, if it doesn't exist, it makes it, right? So when we make our blinky.nim file, so now we have our blinky.nim file. We want our makefile to make a blinky binary file, and that is going to require the blinky.nim file, and it's going to require the blinky or the nim.cfg file. And make will now, every time if you run make and any of these two change, and it tries to build Blinky, it's going to redo this recipe. So we're just going to do a normal sort of build here. We don't actually need both of these. We're going to optimize for size. And the reason I'm putting these flags here is that they don't work in the nim.cfg file for some obscure weird reason. We're also going to be running on standalone OS. That means that we don't try to, or we don't expect any of the OS features to exist, which they won't because we're running on a microcontroller. And we're going to be compiling our Blinky. So if we now run our makefile, it's going to say no rule to make target nim.cfg needed by Blinky. And what that tells us is that it didn't find this file. It goes looking for a recipe to build or to make this file. It doesn't have one. It doesn't know how to get nim.cfg. It fails with an error. So let's make this file ourselves. So for those of you who aren't familiar with nim.cfg, it's not something that we use a lot when we program normal nim. Normally nim c, like nim compile is fine. And the few flags you might want, you just pass on the command line. But for this, we're going to be using quite a lot of flags. So we don't want to have to pass all of these flags on the command line every single time. But they're all the same flags as you might find when just calling nim with arguments. So first off, we're going to be using arc. So previously it used to be the case that we didn't have a garbage collector on microcontrollers. Now we can use arc for automatic reference counting. We're probably not going to be using a whole lot of reference or of garbage collected memory, but it's nice to have there. The CPU architecture that we're going to be compiling for is AVR. This is important to tell it. I had some issues with not passing standalone both here and in the options, or if it was only the options, but we're gonna add it here just to be sure. We're also gonna be using malloc. This is just because the standard library tries to use some features that aren't available in the C library for the AVR. So we're gonna use normal malloc. We're going to be optimizing for size. Again, this is also something I passed in the make file. And now comes all the funky flags. So pass C, that just means send this flag on to the C compiler when you get that far. Nim won't care about these, but pass them on to the C compiler. These are basically pretty normal flags. This one tells the C compiler that we're compiling for the chip. This is just to import C files, or to look for C files we might want to import in this directory. That just helps us if we want to put some C files in this directory later. And then we have a bunch of other things here. This one is quite interesting. This one sets, and now I have to get the amount of zeros right. There, unsigned long. That doesn't look right. Yeah, one more zero there. That sets the clock speed of the microcontroller. The TNC by default it runs at the lowest clock speed it can, which is something like 2 megahertz. It's capable of running at 16 megahertz if you supply 5 volts, which we're going to be doing because we're going to be plugging it in to a USB port. If you run it on a 3.3 volt supply, which it is happy to do, then you probably shouldn't run it over 8 megahertz. You probably can run it at 16 megahertz at room temperature, but technically it's overclocking, so it might be not as stable. Again, we're going to tell the C compiler to optimize for size. I don't think we actually need this. And all of this stuff is basically just, I'm actually going to copy this. All of the stuff that I'm pasting in now is just things that it was in the make file or I got from somewhere else. This, I think, exports things to a list file. I actually we'll try to do without that, because that creates an extra file, which is kind of annoying. We also need to pass some flags to the linker. So this, as you can see, is pass C. These are pass L, so pass to the linker. So in C, you compile stuff to sort of a binary thing, and then you use the linker to link. It's called an object file. So you compile your code into objects, and then you take the linker and link together all those objects. So this is for this part up here is for compilation, and this part down here is for linking. They're pretty much just the same, exact same thing. I don't think we need that. Let's not do that either. I don't think we need those. If it doesn't work, we'll add them back in later. And now the next set of flags here. Oops. The next set of flags here, we don't need this. So this tells us that when we are compiling for the CPU architecture AVR on OS standalone using the GCC compiler, which is the default. So here we give the path to find the tools, the executable of GCC, and the linker executable, which is the same one in the case of GCC. So that just tells NIM which compiler and linker to use. Otherwise, it would be using my system, the default one, which wouldn't know about all of the AVR stuff. We're also going to turn on dead code elimination. We're going to turn signal handling off, like sig int, which happens when you do control C, all of those, because those aren't available to us on this platform and just cause errors. And we're also going to define no main. Basically what that does is that it tells the compiler, don't generate a main function. We're going to define our own main function. So don't worry about creating that for us. So that should make that should make makefile happy. So as you can see, the makefile now happily runs our target, but NIM is compiling that it can't find panic override. And this is also probably foreign for you if you haven't been using NIM for microcontrollers before. Basically what the panic override file is a file that tells NIM what to do in the case of an unrecoverable error. So basically if you have a an interrupt, which we won't because we don't have them. But if we have an exception that propagate all the way to the top, what are we going to do? That kind of stuff. Oops. Yeah, good old panic override. I actually thought we didn't need that on when we were using Arc. I was a bit surprised to find that it's still here. It wasn't there when I did OS any in my testing, but that just didn't work for some other reasons. So we're gonna be using yeah. So here we're just gonna, this is all just something I borrowed from a project that has borrowed it from some other project. So I'm not sure even how applicable all of this is to this particular chip. But it works. We're not gonna write code that relies on this anyway. Basically it needs a way to output stuff, so raw output data to typically a terminal, but we don't have a terminal. We just say don't bother writing stuff out. This exit is just something that I've imported. I'm not sure if it even does anything on the AVR platform. But then it also requires this panic function, which is basically what are we gonna do if the output, or what are we gonna do if we get a panic, so an exception that's thrown all the way up or something similar. Just gonna call exit on that. And this should be all that we need. Panic override, let's see. There. Nope. There we go. Yeah. So now Nim is happy it found the panic override file when we named it correctly. It compiles, but then the C compiler complains that undefined reference to main. So we turned the main function off in our CFG file, and now obviously we don't have a main file or main function anymore. Oops. So what we're gonna do is we are going to create a main function. We're going to export this so that it is available to see. Discard that. So just basically do nothing. And now we can see our file compiles, and we have our Blinky executable here. But if you remember from the part about actually loading code onto the controller, we need this .hex file. So we can't just take this thing, which is an ELF executable. We need the hex file thing. So in our makefile here, let's make a target to make this Blinky hex file. It's gonna require the Blinky ELF, and we're gonna be using a tool from AVR bin utils, which is called AVR object copy, which copies the stuff out from the ELF format and into this hex format that this loader and a lot of other stuff uses. Again, these are just these are flags that I've copied from project to project. We basically say we want to output this hex format. I'm guessing this creates an EEPROM something, or so EEPROM is sort of our storage on a microcontroller. It will store data between reboots. I used this in the Arduboy stuff for saving like high scores. So this basically tells, I guess, the hex file that it should clear EEPROM or do something with it. Not entirely sure. But that should now allow us to type make blinky.hex, and it will make this blinky.hex file for us, which is just text, apparently. I'm guessing this is no. I'm guessing this is, yeah, this is just a hex file, just something that it can read. Yeah. So if you've been doing programming in Arduino, you might be like, when you compile or when you build, you get the sort of like size estimate thing. We can get that on the command line with this. So we specify our chip. This we give the ELF binary and not the hex file. And here we can see that our program takes a whopping 212 bytes. And we don't have any global variables, which makes sense. And we're using 0.6% of the available space. I also like to put this into my makefile. So as I said, these rules are intended to make files. So if I now remove my hex file, and if I remove this file here, and I tell it to make the hex file, it will first make the blinky, and then it will make the hex file. Because it looks at this rule and sees, we need this blinky file, but we have a recipe for making the blinky file, which needs these two files. And then we're gonna run this, and that's gonna run this. I guess we could also add our panic override file to that if we really wanted to. That just means that if we change the panic override file, that will trigger a rebuild of this blinky, which is pretty nice. But we can also do stuff like this. So here I say, if we try to make a file called size, we need blinky. This is not gonna make a file called size. So it's gonna trigger every time we run this rule. We're gonna do that. And now we can say make size. And that gives us the size. And it will also trigger the same rebuild. And if we change the CFG file, this will make that size change for us. We're also going to be making an upload target. So this is the target that's going to be calling the TNC loader. This also has an MCU flag. It's not the same MCU flag that we have here or for the compiler. Since this is the TNC tool, it's just called TNC2. Let's make it verbose so we can see what it's doing and give it this hex file. Now, if we now switch to our cam here, so if we now run make upload, you can sort of barely see it behind the let me move that out of the way. There. So here you can see it's calling this, it is waiting for the teensy. Hint, press the reset button. So if we now take this and plug in this USB cable, it lights up. It already has some code on it. And if we now hit this reset button right there, if I press this, you can see that the half-K bootloader was recognized. It read this blinky, 212 bytes, disagrees a bit about the size, programming, booting. The reason it disagrees about size is probably because this is aware that there is a bootloader. The bootloader takes a little bit of space. So it's going to know that we don't actually have the full capacity of the chip available to us. I can't see these emojis, by the way. But as you can see, on this chip, it's now just sitting there. It's not doing anything. It's not lighting up. It's pretty much, it looks pretty dead. Which makes sense, because all that our code does is just discard. So how do we do stuff on the teensy? The easiest thing we can do is to use the I/O pins. So the I/O pins, most of you probably know this, but on this microcontroller, you can see all around the edge here. All around the edge here, we have these holes. These are our I/O pins. Well, most of them are I/O pins. Some of them are output voltage and ground and stuff like that. And in order to use these, in the Arduino IDE, which you might be familiar with, you would do some like calling pin stuff and stuff like that. But for us, we're going to be using pure C. So we're going to be doing this kind of stuff. And we are going to look at how we're going to be making this easier for ourselves with macros in just a second. But if you look at the chip here, it has, let's get this in focus, it is labeled. So as you can see in the top left, it says F0, F1, F4, F5, F6, F7. You also have at the bottom, you have some B's. At the bottom right, you have some D's. And I think on the top, yeah, all the way in the bottom right corner, you have some C's. And the top right, I guess for you guys, the top rightmost one, it's super hard to read, but that should be a pin called D6. And D6 on this particular chip is the LED. So this microcontroller in particular has a built-in small light emitting diode, or LED, which we can get to light up. So that is D6. These are the registers that we can assign stuff to. This controls the direction. So if it's an input or an output pin, so it's an I/O, all these are I/O pins, input or output. So this configures if it's input or output. And this, if it's an output, then we can say basically low voltage, high voltage. So no no power out or power out. When it's configured as an input, we can either have it normal or with a pull-up resistor. We might get back to that later. And with this register, we can read a pin. So all of these are 8 bits. So they're basically like uint 8s. And we set the bits in these to do the different things. So for D6, we would set the register DDRD, the 6th bit of that. If we set that to output and set port D, the 6th bit to 1, then the D6 pin is going to go high, and it's going to output, or it's going to turn on that LED. So in order to do this, we need to get access to those registries, or those registers, not registries. I'm just going to do a bit of a dirty hack here. We are going to include the AVR IO file. This is basically the definition of all the pins. Then we are going to declare some variables here. So for right now, we only need port D, which we are going to import as port D. The reason, so we could have written this as port D like this, but I don't want it to have a capital first letter, so we're gonna write it like this. And we're gonna tell them to not declare it, just like assume that it exists. We know that it exists because of this line, but just assume that this variable exists. We are also going to need our DDRD, which you remember is controls the direction. Yeah, I know I should use header. That's a good idea, I guess. Yeah, no decal. Okay, so let's actually do that instead. I like that idea. So we're gonna push no decal, and header is like this. And do a pop. Not do that. What is this complaining about? Does that need to be like this? Oh, we had this in this file. Yeah, it's what I had, should have worked. Ah. That's complaining. Right. So now we can avoid using no decal there, and avoid having this emit. So basically what we're saying here, for all of these statements, assume header and no decal pragmas. We can also do the pin. We're not going to be using it just yet, but just for completeness sake, let's grab that as well. So now we have these. What we can do, what we need to do, we need to set this pin, or set this to output, and set this to high. And the way we do that is with bit logic that looks like this in C. looks a bit different in NIM, of course. So we are going to say DDRD is DDRD or one bit shifted left 6 times. So that turns the 6th bit in the DDRD register to 1, making it an output. And we're gonna do the same thing for this. In this case, we could also write something like this, but we're gonna refactor this into something nicer later on. So let's not do that right now. Oops. There we go. So this code should now turn our LED on. So if you go back to the chip cam, we run our make upload, which is gonna rebuild. Oh, we forgot. I know this is behind. Let's just switch back. Yeah, so it was basically just complaining that I missed one of these for my header because I had messed up when I typed it in. So yeah, make upload is ready. Switch back to look at the device here. So when I hit this, it's gonna upload our program and the LED comes on. Nice. Right. Another thing that we might want to do, so if we want to make it blink, we can import, so obviously we don't have like os.sleep, but what we do have is delay ms, which is basically the same thing. This is called delay ms, like this. And this comes from the AVR, what's it called? The AVR delay.h. So now calling this, we can delay. So if you remember, this just sets it up as an output. And this is what actually sets it to high. So if we do this and add a small delay of let's do a second, and you might notice I have a slight smile right now because this is not going to do what we think it's going to do. So now we need to flip this bit back off. Oops, sorry if I hit the mic. Flip this bit back off. So we're going to do an and not. Basically, this shifts the bit 6 bits to the left. This inverts that. So now we have a bunch of ones, 1 0, and a bunch of ones again. And then we AND that with this port. Again, this doesn't really matter in our case right now. We could just set this entire port to be 0, but this is just setting that this 1 bit that we're actually using right now. Oh, sorry, all of that was in chip cam mode. Yeah, so what I did, I import this delay ms function since we don't have os.sleep. So we import this from the AVR delay.h header and we call it with 1000, so 1000 milliseconds. So if we now go to the chip cam, and run make upload. And we hit the button. We can now see that the LED should, after a while, slightly longer while than I was expecting. You know what? We might have done something wrong here. I knew it wasn't gonna take a second. It shouldn't take this long. Interesting. I'm gonna leave that up there. So basically what is happening here is the no, it's fine. As I was saying earlier, the TNC can run on different clock speeds. Yeah, can run on different clock speeds. The TNC defaults to 2 megahertz. If we want to run it at 16 megahertz, we must set the speed. Interestingly enough, delay ms actually delay for 128 milliseconds when the clock speed is this. So the I think that's a typo. It's supposed to be this thing. So when we're running at 2 megahertz, this is gonna take much longer. It took way longer than I expected, and I think something else might be wrong. But basically, we need to set our CPU prescaler to 16 megahertz, which is what we have defined that we're going to be using. So for this, there is a nice macro in the AVR libraries. We're just going to be using that. CPU prescale, it's called, and we're going to be doing CPU 16 megahertz, like so. That is declared in some header, and obviously it doesn't tell us which is super annoying. Yes, I am. Basically, we can just set this to 0. We don't have. Give me a sec. I'm just going to borrow something here. I find I tend to use emits quite a lot when I'm working with this kind of code, because there's just small stuff like this that I just can't be bothered to do them myself. Yeah, so we recompiled, we hit the button, it rebuilds, it turns on the LED, and it turns it off, and it turns it back. It should turn it back on again. actually not quite sure. I'm not 100% sure what's going on here. Because this, oh, wait. We need a second wait. That should have done the opposite thing though. Yeah, so now it's lighting up. Oh, yeah, there we go. So yeah, as you can see, 1 second off, 1 second on, 1 second off, blinking. Nice. So that's nice. Yeah, amazing. What isn't quite as amazing is this code. This is completely unreadable, or not completely unreadable, but it's not the best. So let's do some macro magic, to make this work better. So first off, we're gonna do this. We're just gonna define all of the ports. Oops, that was a bit too aggressive. We'll do these in there as well. Right. There aren't any B's, so let's do this instead. There, and we have a port F. Yeah. That is just all of the different pins, or at least spaced by the actual port letter. How many? What are the names of the ports? We have C's, we have D's, we have B's. Oh no, wait, this is another chip. Damn it. That's not the chip that we have. Yeah, so we have B's, we have D's, we have AC, we have an F, and we have an E over there. So we are going to need C and E as well. There. That just defines all of our ports. Now let's make a macro here. So as you can see from this, as you can see from this, not all the pins on all the ports are available. So we have 0, 1, 2, 3, and then we have 4, 5, 6, and 7 for the B port. So the B port is full. We have D, 0, 1, 2, 3, 4, 5, 6, and 7. So port D is full. F is 0, 1. F is 0, 1, and then it jumps 4, 5, 6, and 7. So F2 and 3 aren't here. They are possibly used for the USB. Yeah, B we've already gone through. C, we only have C7. And E, we only have E6. So what I'm thinking is that we define our ports, or we define all our pins, and then we write macros to spit out these things for us. So the goal here is to be able to do sort of like D6 dot high and D6 dot low. Basically all of the pins that aren't available to us are used for stuff, like other stuff, be it the USB or maybe something internal, or I don't know. There are actually some pads on the back as well. None of those are data pins though. Yeah, and the pins, these 3 holes here, they're labeled on the back. They're not labeled on the front because there's no room for it. They are reset. So I think shorting this to ground is the same as pushing this button. This is ground. Yeah, so if you short these, that's the same as pushing this button here. And this is a VCC, so a power out, same as this pin. Just a little bit of convenience to have them over here as well as over here. And this one, which also isn't labeled, is what's called AREF, which is analog reference. So this thing has digital or analog to digital converters. So if they have a analog sensor connected, we can read the level between 0 and 5 volts, and that is in reference to this pin. Just we're not going to be using that for this, but that's what those are. But yeah, so the goal is to be able to do something like this, and of course something like this, right? And those are going to be doing these things. So let's model this in a type. So this, since we're going to be using these in a macro, this object is never going to live in code that runs on the controller. So we can just put whatever we want in here. I'm going to put in the port as a string, actually as a character because it's a single character, and the number of the pin as an integer. Now we're going to define these constants. So all of the pins, we're going to define them as constants. So we remember B, we have all the pins for port B. So this is going to be B with the number of pin 0. Do we want to make an initializer for this? I guess we might as well. So port num. And this is file time. I'm just gonna do this. Just so we don't have to type port and pin all the way. I'm not sure, can we get away without doing that? This doesn't work, right? No. Yeah, so B1 is pin B1. This is 2. This is 3, 4, 5, 6, and people are messaging me. And 7. We also had all 4. That was 3. We also had all of the D pins. So let's do this and just do a little search and replace B for D. So we had all of the D pins. We only have, yeah, so we're missing 2 and 3 for the F pins. So we're missing 2 and 3 for the F pins there. E pins, D pins, and for, oh, okay, we actually have 6 and 7 for C, and only 1 for E. So 6 and, wait, what did I say? 6 and 7? Yeah. What have I done here? No. C7. This is going to be C and 6 and C and 7. We're going to chuck this into a library at some point. By the way. There. So now we have defined all of our pins. These are all of the I/O pins that we have available with their pin number and their port name. So now we need to write some macros. So let's start with this output one. Macro output pin, and this is going to be a static pin. So most of you probably know, but in NIM macros, if you just do this, it's gonna expect something that at runtime will be a pin. Our pins are never gonna exist at runtime because we don't want to store all of this information in our program. So we are gonna be taking these in as static pins, which means that what we're passing to the macro is actually gonna be a compile time valid pin definition. That is also why we have defined them as constants, because then we know that they are available on compile time. We don't need to take anything else. It's going to be an untyped thing. Now we need to make our port from the single character in our pin. So we're just going to make a new identifier node. This is going to be, so for outputs, we need to set the DDR port. So DDR, or this is name code, so casing doesn't matter much. And this is going to be pin.port. We're also going to extract this this number here and make a new literal out of it and assign that. So now we have port, which is this, and we have num, which is this number right here, which means that we can do a simple quote do. For that to work, we obviously need to import macros, like so. Down here, we now output our port is equal to our port. So basically the same thing that we're doing down here. Port is equal to our port, or 1 shifted left num times. Right? So now the D6 output should do what we expect. Similarly, we can make our high and low macros like this. High is going to be the same. We're setting it to a 1. This is not going to be the DDR register though. This is going to be the port register. So remember down here we said port D, and not DDR D like we did here. And same for this. This is also going to be port, but this is going to be that and not to unset that pin. And now all of our warnings went away. We can remove our comments. And if we now run our code, it's waiting for me to press the button. Let's switch back to ChipCam. You can see it's still happily blinking along, just running the program that we put on it. When I hit the button, you're going to see in the background that it reprograms, and it's still blinking a little light. Great. We can also see 264 bytes. It did. So you can see here all of our, we're not using our stuff. That's fine. It's using 264 bytes. The previous time that we ran it, we were also at 264 bytes. So going from doing this logic inline here to this D6 output, D6 high, D6 low, didn't cost us anything. Totally free. Not a single byte of overhead. We're not calling a function. We're not doing anything. The code looks exactly the same. And to really just nail that point home, we can have a look. This is actually called Blinky. We are running it in release mode. We can have a look at this file here. Just as you can see, this is quite a bit younger than I expected it to be, but not. Didn't it actually recompile it? Let's remove all of these blinky cached things. I'm gonna remove blinky.hex. I'm gonna remove blinky. I'm gonna make just make the blinky. We can do make size. It will tell us that the size is 264 bytes. That is off the binary that we just built. If we look now in the cache, we now have this Blinky folder. This file from right now, we can go and have a look at the C code generated, and we can see that the code that we're spitting out doesn't have one single indirection. It's exactly the code that we had earlier. Even the shift. Oh, I keep forgetting to move that away. Yeah. So as you can see, even the shift operations are already done for us before we reach C code. So the C compiler would do these for us anyways. These shift things. That actual shift operation wouldn't make it into the code. But here nim has already done it for us. Pretty cool. And our code now looks much better. We could of course get rid of this at some point as well. But let's make inputs. After all, we're making a keyboard. We will at some point have to read stuff from our pins. But we see like we have a lot of common code in here. So before we do that, let's just make a small template to expand our thing, or our definition of pins. I'm gonna do this. This is gonna just take this register, and this is the DDR register. So basically this template, it takes in the register because we have to define these different ones, DDR, port, and later on pin. This is dirty, so these are just dumped directly into here. There's no checks of any kind because we don't really need them. I mean, we could have defined one that did the quotes do part as well, but it's not. We're saving a little bit by doing this. There. Okay, so now if we want so now these are outputs. If we want these to be inputs, we can do this. We can create our input function. Oops, input. It's also going to be working on the direction register, but this is going to be doing the and not thing. We are also going to need, so if you look at our not this one. So this is for configuring input or output. This port X, we're using these to do low and high, but we're also using them to do normal or pull-up resistor when this is 0. So we are just going to define one called normal. Not sure why I didn't just copy one of the other ones. Also going to need one. Okay, so let's do. So normal is the same as low output. You know what? We could actually just call low. This could just be a template. Normal and pull up. which is obviously going to be the other one. So as you can see, normal and pull up just does the exact same thing as low and high, because that's what they're supposed to do. We could add a check to check if DDR is input or output, but we don't really have a way to throw errors. We could do like compile time, but we might want to, and we are going to have to, switch pins between inputs and outputs. So we can't do all of that checking on compile time. We could, of course, do something with blocks and try to make some logic, but we're not gonna bother with that. What we are gonna do though, just to check that all of this is working. So right now, this is still just blinking away happily, with that one second delay. But we're making a keyboard, so we need to be able to take inputs. So let us keep, so D6 is output, that is our LED pin. You know what, let us actually just also say that LED is D6. It just allows us to write LED, LED, and LED. Just looks a bit nicer. It does the exact same thing. But now we're gonna do E6. We're gonna say that's an input. We are gonna say it's a pull-up. That means that so instead of giving it a high voltage from VCC, for example, it's gonna be pulled high, and we need to pull it low by connecting it to ground for it to change. We haven't defined our reads yet. So reads, this pin, so this pin register is gonna have all of the values of our digital pins set to whatever they are. And we have to just mask out what we want from them. So for this, we can have our read, which is also going to be taking in a pin, like so. We're going to expand the pin definition to pin. And remember, we did grab these pin, like pin C, pin F, pin B, and pin D. As well. So we're gonna expand, so get our port and our num for pin. We're gonna do quote do, and we're not gonna, so in these we set it to something. We're not gonna do that here. Here we're gonna just read it. And what we want is we want to do an AND check. 1U8, shift left by number. So this takes in, so our port might look something like something. So in this case, this pin is high. This would be pin 1, 2, 3, 4. So it's pin 0, 1, 2, 3, 4. So in this case, it would be pin 4, which is high. And this just masks out that 1 bit. So now, instead of doing this, we can say if e6.read, so this is gonna output a number or 0. The number is based on the port. So we're going to say if it's not 0, then we're going to do something. So it's going to be pulled up, since we defined it as a pull up. So it is going to read as 1 until we do something with it. So if it's not 0, then it's not something. So we are, so then we haven't connected it to anything. So we're gonna say LED low if we haven't connected it to anything, or if we haven't connected it to ground. Otherwise, we're gonna do high. And just to prevent us from running this in a completely busy loop, we're just gonna wait 100 milliseconds, which should be plenty for us to, like, it should feel pretty much instantaneous to us. Make upload. So back to the chip cam. If we now hit the button, you can see in the background it uploaded, and now this isn't doing anything. Riveting. So I'm not sure how well you can see that, but right next to the ground pin in the top right hand corner is B0. If we take a little wire, this is just a normal breadboard wire, and just jam it into the ground hole there. I'm just gonna put a little bit of tension. There's no smoke because we're doing everything right. So we have it now connected to ground, and if I now touch this B0 with this wire, let's see, kind of hard to do. Oh. It's not working. I'm just going to double check that this is B0. Yeah, it's B0. And it was B0. Oh. So if you look at my code, I've written B6 instead of B0. So B6 is... Right, okay. Wait, why do you have my mom's number? Don't answer that. Right, so connecting this to ground, and B0 might be hard for you to see, but it's right down by, like, right next to F7 on the bottom. All the labels are upside down, which is a bit annoying, but it's all the way down here. I'm gonna try not to get my fingers in the way. Right, so it should be this pin. You can see this, and you can see the LED. Should be this pin right there. And it's too bright for you to see. So if I touch this pin, there we go. It's really hard to do. Yeah, touching the pin, LED turns on. Now my finger's in the way. Okay, I'm gonna do this from the back. No lewd jokes about that, please. So, oops. There you have the chip. If I now touch, oh, there, that's B0, B6. So whenever I poke this wire through B6, you can barely see the wire at the bottom as I poke it through. Oh, I say barely, it's pretty visible. Yay! So now we have basically a one key keyboard that is turning on and off an LED for us. So we have a lot of code, most of it for doing binary keyboard, what real programmers use. So we have a lot of code here, mostly just definitions of our ports and our pins, and code to like macro stuff that doesn't do anything on runtime. And it all boils down to being able to write a main function that looks like this, which, at least to me, is pretty nice and readable. We could also obviously define like on and off for these if we wanted to. And we could write a read that returns a boolean. The only thing sort of that this approach lacks from the C part is that since these are just binary operations on ports, if we want to say make all of these pins inputs and make all of these pins outputs, we wouldn't have, so in our code we would have to do something like B6 is an input, B5 is an input, B4 is an input. We could maybe do something like this. I wonder if this works. Yeah, no, because this isn't. We can't define this. This loop can't be compile time. At least not. Might be a way to do this, but yeah, and that would, either way, that would still run these OR operations once per pin, which would be super annoying. It wouldn't look good. But we can of course write a macro that does something like this and just accepts multiple pins. We could even write stuff that does something like this. Takes a range or a set, maybe. Maybe that could be nice. So we could say 0 to 3 and port 7. That is something we could do. And it could combine this on compile time into the mask, and it could write that to this thing. This might be something that we do when we get into actually doing the keyboard stuff, because it might be more usable for us. Again, it's going to be a zero cost abstraction, so we don't really have to worry about how complex it's going to be on our keyboard. But yeah, that is the beginning of our Teensy firmware in NIM for running the keyboard. I think I'm gonna cut it there. We are currently at 1 hour and 3/4, which is quite a long stream. So yeah, I think we're gonna cut it there, and next time we're gonna look into actually doing stuff with the matrix. So it's called a matrix when you have, these are all wired up in columns and rows, and the way all of that works I'm gonna explain next time. And we're gonna look into how we can do that in Nim. And then when we have all of that working, we are probably gonna look into doing the one on the IO expander, so we can have them both working and talking to each other. I might actually rewrite these or rewire these so that they're both using, so that both halves have an IO expander, and then I have one microcontroller with sort of a Y split thing. Ooh, dark red on gray is hard to read. That is a good point. I've just sort of gotten used to it. I have been thinking about changing my entire setup, like color wise. If you have any good tips for color schemes, I'm all ears. But yeah, so what I might do is when we start getting to the IO expander, we're probably gonna go back from programming on the matrix to programming on this thing. I have another IO expander, so we're probably gonna hook the IO expander up, maybe with just some of my spare keys. Maybe we're gonna do something else. But get the IO expander working. If that works fine, I might rewire the keyboard halves so that they both have one IO expander each. And then we're gonna have one microcontroller that sort of only communicates over I2C to the two IO expanders. In which case, the teensy is super overkill because it has a lot of pins that we're not using. We might use those to connect something else, maybe a little screen, maybe nothing. Maybe I'll even swap it out. I have a Bluetooth, I think it actually is the same chip, but it has a Bluetooth radio built in. So we could look at just porting the code over to that, and maybe we can do this as a Bluetooth keyboard with battery. But yeah, so when we have that, the IO expander, all of that talking together, then we're gonna start doing usability stuff. So macros for layouts, the way so all of this, the normal keyboard firmware is obviously typically written in C, which looks like C always does, a huge mess. I want to do something. Let's do this over in this file so we actually have highlighting. I want to do something like you just define your layouts as simple as this, you know. What is that, UIOP or something? I'm using Dvorak, so this isn't my layout. ASDEF? No, that's not. FGIH. But then the I can't be up here. No, the I is up there. This is a J. JHKL. Something like that. UIOP, yeah, ASDF, FG, JKL, JKL, yeah, and then it's Z, X, C, V, B, N, M. And some special keys, obviously. So we might do something like this, where you can define your layout super simply in a macro, and the macro just turns this into whatever format that works. Of course, then, so many hobby keyboards probably because people can't be arsed to solder up a full size keyboard, or to just like 10 key less. Typically, a lot of people have what's called layers. So you have some keyboard shortcut you hit on the keyboard that changes all of the keys to a different layer. So we could do like you can name your layers, something like this, and then we could do waffle hands, and then we could do switching between the layers super easily. But yeah, that's the idea anyways. Make it super easy to configure, super easy to work with, super easy to write your own sort of extensions to it and expand on this. And hopefully we're gonna take over the world of custom keyboards, because this is much easier than C. So yeah, that's pretty much what I had today. We're gonna be back with part 2. Now we are in super lockdown mode here in northern Norway, unfortunately. So I have a bit more free time because I'm not doing other stuff, meeting people and climbing and having other kinds of fun. That sounded sketchy, but so I have a bit more time for this kind of stuff now. But I'm not sure when the next time I'm gonna stream will be. Hopefully either this week or next week. But yeah, that was what I had for today. Not, yeah, unless any of you have any questions, I think we're just gonna cut the stream there. I am thinking of sort of cutting this into a sort of shorter, neater format. Maybe do some like voiceover explanations, maybe add some drawings, and make like a proper YouTube series out of it. So this is only streaming, it's not recorded, it's not gonna go directly up on YouTube. So if you want to see these streams raw, live, and unedited, you have to watch them. You have to watch them live. If I don't end up editing any of this, I'm just gonna upload this to YouTube. But hopefully I'm gonna sort of cut it up and make some nice videos to show people on YouTube. So yeah, that's all I had for today. Hope you liked it. People seem to. And I'll be back with more hopefully soon. Goodbye.